Let's study effectively with MISI CT Skill Builder. In this video, we will see how binary digits can represent sounds so that computers can process and store them.
Have you ever stopped to think about the sound you're hearing right now? How it travels from my voice through the air and somehow ends up perfectly preserved in a file on your device? Well, today, we're going to pull back the curtain on that incredible, invisible journey.
I mean, really think about it. You've got an entire band, maybe even a full orchestra with all its complexity and power, and it all gets squeezed into this tiny digital file. It feels a little bit like magic, doesn't it? But it's not magic. It's a fascinating process of translation from the physical world into the digital one.
Okay, so first things first, we have to understand what sound really is. Every single sound you hear, from a pin drop to a thunderclap, is just vibrations traveling through the air. These vibrations create waves, kind of like ripples in a pond, that move through space. This is sound in its purest, rawest form. Now, these waves have a couple of key features. The first one is called amplitude. And honestly, it's super simple. It's just the height of the wave. The taller the wave, the louder the sound. The shorter the wave, the quieter the sound. That's it. Height equals volume. The other key feature is frequency. If amplitude is about height, frequency is all about width. So, if the waves are all squished together and happening really fast, you get a high-pitched sound, like a flute. But if they're stretched out and lazy, you get a low-pitched sound, like a deep bass note. So, width equals pitch. So when you look at a sound wave drawn out like this, you can literally see how it all works together. Its height, the amplitude, goes up and down, making things louder and softer. And its width, the frequency, changes, making the pitch go higher and lower. This smooth, flowing line, that's the original, perfect analog sound. All right, so we've got this beautiful, invisible wave just floating around in the air. The next huge question is, how on earth do we grab it? How do we take that physical wave and turn it into something a computer can actually work with? Well, it happens in a few stages. First, those sound waves hit a microphone. You can think of a microphone as basically a mechanical eardrum. It feels those vibrations and turns them into a tiny electrical signal. Then, that signal gets sent to a super important piece of gear called an analog to digital converter, or ADC for short. And this is where the real transformation begins. This brings us to the core of the whole process, something called sampling. Now, the best way to think about sampling is to imagine you're taking a super fast photo shoot of that sound wave. You're taking thousands of little snapshots every single second to try and build a digital picture of that original smooth wave. So that ADC, the analog to digital converter, is measuring the wave's electrical voltage at incredibly precise, regular moments. Each one of those measurements gets turned into a binary number, a simple string of ones and zeros. It's basically plotting points along that smooth curve and giving each point a numerical value. You can see exactly what's happening right here. That smooth blue line is our original perfect analog sound. And those vertical red lines, those are the samples. That's the ADC taking a snapshot of the wave's height at that exact moment in time. It's turning that continuous flow into a series of separate, countable numbers. But how good is that digital copy going to sound? Well, that all comes down to two really important things. First, how often we take those snapshots. That's called the sample rate. And second, how much detail we capture in each snapshot. That's called the bit depth. Let's see what happens when we use a low sample rate. If you don't take very many pictures, you end up with this really blocky, jagged-looking wave. It's like trying to draw a perfect circle by just connecting, say, 4 or 5 dots. I mean, you get the basic shape, but you've lost all the smooth, beautiful curves. But now, look at this. With a high sample rate, we're taking way more snapshots every second. And suddenly, the digital version is a much, much closer match to the original. We're connecting hundreds of dots now, and that circle is starting to look practically perfect. More samples means more detail. It's that simple.
And when we say high sample rate, we are not kidding. For the music you listen to on a CD, the sound is sampled 44,100 times every single second. That number seems random, but it's not. It's about double the highest frequency a human can possibly hear, which guarantees we capture all the sonic detail our ears can even process. Okay, so that's one half of the quality equation. The other half is bit depth. If sample rate is how often we measure, bit depth is how precisely we measure. Imagine you're trying to draw a picture. A low bit depth is like having a box with only 8 crayons, but a high bit depth is like having a box with millions of crayons, letting you capture every single subtle shade.
And the numbers here are just mind-blowing. A standard CD uses 16-bit audio, which gives you over 65,000 possible levels of volume. But a 24-bit recording, like for a DVD, get ready for this. It gives you over 16 million possible values for loudness. That creates this huge dynamic range, capturing everything from the quietest whisper to the loudest explosion with incredible accuracy.
And this all leads to the great trade-off in the world of digital audio. For something like music, we want that high sample rate and that high bit depth to capture every single nuance. The result is beautiful, high-fidelity sound, but a really big file. On the other hand, for a voice call, we don't need perfection. We need speed and clarity. So we use a much lower sample rate and bit depth. The sound is less detailed, for sure, but the file is tiny and easy to send over the internet in real time. So, that brings us to the final question. Why the huge difference? Well, it all comes down to complexity. The human voice sits in a pretty narrow range of frequencies, so we can get away with taking fewer snapshots. But an entire orchestra with its booming drums and soaring violins covers a massive range of sound. It just needs way more detail to be captured properly. It's all about choosing the right tool for the job. And that, in a nutshell, is how sound becomes a file.
Thanks for watching. If this helped you clear up the concept, hit that like button and share it with a friend who might be struggling with it too. Let's build those skills together.